Good morning, everyone. Welcome to the April Friday Forum. This one is entitled Understanding the Characteristics of Hailstorms and Hail Damage Through Laboratory and Field Research. We're very happy to have Dr. Tanya Brown-Giamanco and Dr. Ian Giamanco, both from the Institute for Business and Home Safety. Dr. Brown-Giamanco is the Director of Hail Research and the South Carolina High Wind and Hail Underwriting Association Endowed Hail Chair, and is also an adjunct research faculty associate at Texas Tech University. Dr. Ian Giamanco is the lead research meteorologist at IBHS, and they're going to be talking about some of the excellent work that has been going at IBHS on hail research and hail risk reduction. While I have everyone on the line, I want to remind people that we'll have our upcoming forecast webinars in May. On May 4th, we'll have Carrie Anderson talking about the wildfire forecast for Canada for this year. And on May 30th, we'll have Bob Robichaux talking about the hurricane forecast. So you can watch your inboxes for some more information about those upcoming webinars. For the presentation today, we'll be using the question function in the webinar software for questions. So if you'd like to ask a question, you can ask a question anytime throughout the webinar. We'll save all of the questions to the end of the webinar, and we'll have a discussion at the end. The question box is in the control panel, which should be sitting on top of your screen right now on the bottom right. If it's minimized, you can press that orange button and access the question box. And again, feel free to ask questions anytime throughout the webinar, but we'll hold all the questions to the end. And with that, I'll pass it to Dr. Brown-Giamanco. Thank you very much.
So thank you for having us on today's forum. We're excited to talk to you again this year about some of the research that we've been doing. Some of the things that we've been working on are similar to the last time I spoke to you, but we've taken some significant advances in how we do our laboratory testing and some of the information that we're collecting in the field. So we will go through those things, and hopefully you'll find everything we have to say pretty interesting. So I'll start out by talking about IBHS. For those of you who have not seen our presentations before, we are a nonprofit that's funded by the insurance industry. Our membership is made up of primary insurance carriers, reinsurance carriers, and risk modelers. And we're charged with basically being the scientific research organization to represent those groups. And here's our mission statement: to conduct objective scientific research to identify and promote effective actions that strengthen homes, businesses, and communities against natural disasters and other causes of loss. So we're really trying to take a scientific approach to understanding these issues and coming up with solutions that are realistic and applicable and will help drive those losses down, which of course is good for the insurance industry, but it's also good for policyholders as well. So what we're going to talk about today, we're going to kick things off with a weather-related risk overview to kind of talk about the hazard as a whole. We'll talk about our IBHS field measurement program, which we've been doing for 4 years now, and we'll be starting again in about a month from now. We'll talk about overall building vulnerabilities to hail, specifically asphalt shingle impact resistance. We'll also talk about loss mitigation opportunities and a new collaboration that we've been working on with the roofing industry to develop some best practices. So to start things off and kind of give us a little bit of framework, we'll look at the overall insurance industry implications. There's a couple of sectors of the insurance business that really have a stake in the game as far as the research that we're doing. So first, of course, is underwriting. If we can understand product and building system performance and communicate that information to the insurance industry, then they can, through their own business practices, come up with better ways to underwrite against the risk. If we understand the risk and we understand the implications on the built environment, that's a step forward we can definitely take in underwriting. On the pricing side of things, being able to understand that interaction between the weather and the overall built environment can help set the correct pricing and make sure that the risk is adequately accounted for. On the claim side of things, a lot of the operations that we're doing help identify what real damage is or what damage that will cause further problems down the road, perhaps defining the difference between cosmetic and functional damage. All of those things go into providing tools for claims adjusters to help them do a better job at understanding, what components need to be repaired, what might need to be replaced, and how much remaining life is available. And last, identifying and reducing fraud. This is particularly a big idea in the world of hail. There's a lot of additional costs and additional claims because of extra activity, whether it's contractors or occasionally building owners. There's indications that the amount of losses are being inflated by some of these parties. So I'll start out by talking through some of the basic statistics from last year and then kind of the overall trends in the industry. We, of course, are based in the U.S., so our numbers are based on U.S. figures. But the Canadian market, with regards to hail, should follow suit pretty well. You guys have a pretty active hail corridor in the center part of Canada, so I would expect the overall trends that we see here in the U.S. would probably be reflected in Canada as well. So 2015, the overall losses in the U.S., this is overall insured losses, 25 billion overall, and 15 billion of those were insured. Specifically in 2015, the winter storms were kind of one of the leaders, an area that we don't typically have as a leader of losses in the U.S., but there were some pretty significant events in early 2015 that really caused those numbers to drive up. Severe thunderstorms, of course, is a peril that's always around. It's one that's there every single year. It doesn't really go away. Almost $10 billion of insured losses. And drought, as we continue to see drought increasing in certain areas of the country, drought is also leading to some large losses. So these were the three primary categories that affected the market in the U.S. in 2015. No big hurricanes, of course, no big earthquakes of any substantial amount. So these three perils, the thunderstorms are pretty much always there, but the other two are a little different than normal. If we look at some overall trending of the industry, this is from Munich Re. They put this slide together based on the newest data that came out for 2015. And what you'll see is an overall increase in the amount of losses that are being put on the insurance industry over the last 30 years, 35 years. And you'll notice that not only is the overall trend increasing, but the trend for the meteorological events, which is those shown in the green, is increasing as well. And that's the area where our hail risk is captured. So the number of losses are piling up. A lot of it is the result of increasing population and increasing stuff, increasing infrastructure and buildings and things. As the population density increases, there's just more of those things available to damage in an event. So we see those losses increasing over time. And really, without a significant mitigation, I think we'll continue to see that happening. So if we look at some overall statistics for the industry, this is an annual set of averages. This was compiled in 2009 by Sheng Nan, a researcher at Illinois. And this just kind of shows some interesting things about how damaging hail really is. So if we look at an average annual year in the United States, the number of days that hail occurs at the level that damages crops is 158 days. So getting close to half of the year, not quite half the year. The number of days in which there's property damaging hail is 123. If we look at the losses, the crop losses on average from his paper were about 580 million per year, and property losses were about 850 million per year. That's an interesting point to point out. A lot of the hail research that started in the United States was a result of the crop insurance industry. They funded a lot of the research. They were behind a lot of the research in the 60s and 70s in particular. Back then, about 40 to 50 years ago, crop losses actually outranked property losses due to hail. But that trend has since changed, and property losses are now higher than the crop losses. So one last stat, at least 13 days per year when crop losses exceed $1 million, and at least 15 days per year when property losses exceed $1 million. So the losses are definitely driving up. All right, I'm going to turn it over to Ian now. He's going to talk a bit about our field research program and some of the things we're doing to understand the hail hazard and hail characteristics a lot better.
Thank you, Tanya. Our field research program was really driven by the need to collect certain information regarding hailstones and hailstorms to guide what we're doing in the lab. Tanya will cover this a little bit later in the webinar when she gets to the section on laboratory impact testing. But both of us have pretty extensive experience in meteorological field campaigns. So we kind of scoured the literature and spent some time really digging to figure out what we need to know and what we need to measure to really reproduce the characteristics of hailstones in the lab so we can make impact tests about as representative as we can get. What are the things that we need to know? And up on this first slide here for me is we need to understand the kinetic energy. We kind of intuitively understand that hail damage will scale with the amount of energy a hailstone hits an object. Related to that is also the size and mass. So understanding the shape, how that affects the aerodynamics. What is the difference in mass between spherical stones versus very, very inhomogeneous shapes, and how strong hailstones are. Throughout really historical literature and even kind of day to day when you hear about a hail event, a lot of people talk about hard hail, soft hail, slushy hail. Well, what does that mean? Is there a number to go with it? So figuring out how we can capture that and then take it back to the laboratory was kind of an important piece that we needed to collect. So really the idea was to just safely collect measurements of the physical properties of hail. So that's the measurements of their dimensions, the major diameters, their smallest diameters, the strength, and really understanding how much of what kind fell within a hail swath. So there's a nice graphic just showing how we would go about doing this. We would trail behind a thunderstorm, quickly enter the swath of hail and collect stones and make measurements of their properties. We also have some other tools that we can use, such as a deployable in situ probes that we could set up in a network in advance of a thunderstorm and let the thunderstorm pass over the probes and collect information on the impact energy, the distribution of impact energy over time, and then we can work backwards toward looking at size distributions and concentrations. So really the concept is to learn a lot just by looking is really the idea behind it, that we needed some information. Let's go take our tools out to the field and measure the components or measure the properties of hailstones that we need. So we'll take a look at a little bit of the data and kind of hop to some results that we've gotten. The first plot on the left of the screen here, we're looking at the diameter to mass relationship. And we plot this up really just to show hailstones kind of depart from perfect spheres a little bit. The yellow line is an actual perfect ice sphere of a density of approximately 0.9 grams per cubic centimeter. That's a clear ice value. And the general trend, and it is definitely noisy, is kind of a departure from that perfect sphere, although we kind of get two splits. We have some data points out in the larger hail sizes that fall closer to perfect spheres, where some of the giant stones, as you see, as we get over 6 centimeters, really deviate quite substantially. So that makes a difference in how we look at the aerodynamics of hailstones, and I'll come back to that in a little bit. The plot on the right is actually looking at a hail shape factor that was used in a paper by Charlie and Nancy Knight many years ago, but it's looking at the minimum dimension with relation to the maximum. So a value of 1 would mean it's close to a spherical shape as you can. And as we look at that with respect to the largest diameter, we kind of generally see a movement away from that perfect value of 1, or really what we see is the large spread that hailstones take on these variety of shapes, and they're definitely not spherical. And applying some assumptions that are associated with spherical shapes may not be the best approach to keep impact tests as realistic as we can make them. I wanted to show briefly just a tool that we'll have to even get more information on hailstone shapes. Last September, we took a laser scanning system, a handheld 3D laser scanner, out to the field, and for the first time captured a digital 3D model of a hailstone. So we can get very high resolution, high accuracy 3D models of hailstones, which really kind of opened the door to examining shape far beyond what you can do with just physical measurements of, say, 1, 2, or 3 dimensions. We can really start to look at those inhomogeneities about hailstones, get a very accurate density assessment, and then perform later tests. So very neat application. I wanted to make sure I got this in here because it's kind of a milestone for us in the research program. But what we can do is take all this information and look to apply it on the kinetic energy side as well. A recent paper in 2013 by Andy Hemsfield and Robert Wright really took a new stab at how we capture and evaluate the aerodynamic drag on hailstones. A lot of the impact test kinetic energies are based on essentially the drag of perfect spheres. It goes all the way back to a study by Wilhelm and Ralph in 1937 that was applied on the engineering side by Laurie. That's the 1960 reference. And it's been in use since. No one's really evaluated the standards, come back to look at it with much scrutiny. So Andy and Robert really dug into this aerodynamics and really found that there were some issues, and there's some better ways to evaluate the drag on hailstones. Well, then we took our very large field catalog and looked to apply that work. So I've got the kinetic energy equation. This is a little bit of math I guess we'll show today, just showing the dependencies of some of the variables there. So mass, again, the density is what really drives it, but the departure from spheres, that's the shape factor there, and then velocity there. I also missed the squared there, it's under the arrow, but that's also dependent on the mass as well as the aerodynamic drag, and that has to do with the shape of hailstones. And what we ended up with, and I didn't plot all the data on here, I just used the fitted curves. It's a little tough to see. The result of applying what Andy and Robert did in their 2013 paper to our field data, where we have a very large catalog, almost 2,800 hailstones, where we have multiple dimensions in the mass captured. We actually see these two center curves. The blue line, that's the median. So what we're looking at is kinetic energy versus diameter. So we're on the log scale on the y-axis, just to make it a little easier to see. So we have the median of our field database, the kind of orange color, that's the mean. And then the standardized test kinetic energy. So we've got the FM4473 ice ball, the kinetic energy that's used there, the UL2218 steel ball drop, and then the original Laurie studies actually kind of buried in there. But the point to take away is that there's a shift, that what we found was the mean and median has shifted slightly lower. So impact kinetic energies, as a result of some of these varying shapes and a little bit higher drag, were actually lower by a small amount. But what was kind of the big thing that we were able to do because of the large data set was to actually put a spread on there. We could look at the percentiles and really see what the range of possible kinetic energies was. And you can see as we get up to almost the 90th percentile on the top dashed line here, above the standardized test curves. And then we come all the way back to a significant departure when we're looking at, say the 10th to 30th percentile. So very, very interesting, and it's kind of an application of what you can do with a large data set. Now, I should mention that the drag assumptions, they're theoretically based. We still struggle with getting a large amount of in situ measurements of kinetic energy. And that kind of takes me to my next slide, is the idea of using an adaptable network of probes to capture some of this. This is a hail impact disdrometer you're seeing, and disdrometer is a big word for simply any instrument that captures particle size distributions. And we developed this platform here. It's actually based on a NASA design from the early 2000s that was a fixed platform. We adapted some of the data acquisition components, and really it captures the impact energy and its time variation from a hail event. And we can work backwards to apply some of the functions that we did in that the kinetic energy paper to work backwards to get a size estimate. But it also gives us these kinetic energy distributions that we can look at. We can also compare with conventional hail pads and our own physical measurements to see how accurate these are. But it's applying this adaptive network to capture a large amount of data, again, going to the event to get the information we need. And here's kind of what it looks like. It is Scientific storm chasing at its best, and I'm going to click through a few radar images. This is actually a supercell thunderstorm in West Texas from this past year, 2015. And kind of what it looks like as the thunderstorm approaches. At this point in time, about 15 minutes later or so, we have 2 probes deployed. We add a few more as we jump ahead, and then we finish up and we scoot ourselves down to the south and get out of the way and let the thunderstorm roll over our array. In this particular case, the southern 3 probes, it's hard to see, but that's 104, 105, and 106 were successfully able to capture hail from this particular thunderstorm. And we actually made measurements further to the south of hail within this supercell. The other piece of the puzzle, hard hail or soft hail, is understanding the strength characteristics. That's what we need back in the lab and be able to reproduce in terms of impact testing. And what I'm showing here is actually a scaled measure of the compressive strength of natural hail. And we actually scale it by the mean value of the FM 4473 pure ice test. So that's a distilled water ice sphere that we crushed. We measured the amount of force it took to crush that stone, and we took the mean value. And in this particular case, natural hail on average was slightly stronger than the average ice sphere. That was a little not intuitive, but it simply was because there's a lot of variability when you make ice according to the FM standard, which is using injection molds and putting them in, say, a freezer. There's microfractures that you just cannot reduce, and that affects the strength of the ice you produce. So there's a large amount of variability, and it kind of argues, if you're using that type of impact test, and Tanya will talk a little bit about this later on, that you need large sample sizes to really accurately assess the impact resistance of a product if you're using this particular standard. But for natural hail, we see a really, really wide range. The tail is very long on the right side there, and we go all the way from slushy, essentially, where we couldn't test it, all the way out to some very, very high strength values. And in general, the smallest stones are actually some of the strongest. It's not the big giant hailstones that have some of the highest compressive strength values. So kind of an interesting find there. We actually published a lot of this work in a journal of atmospheric oceanic technology paper in 2015. So I'd invite you to take a deeper dive if you wanted to on some of the strength work. Some of the questions we have, you hear this a lot, does more dense equal harder? Well, that's a question we really don't know right now. We're going to use the 3D scanner this year to try to answer that, where we get a very accurate density. We can do a strength test and look at that relationship. Are they really related? What is going on? In the lab, we found that we can actually change the strength without changing the density at all. So very, very interesting find there, but does that relate to natural hailstones? And the hypothesis we've kind of put together and are going to tackle is hailstone strength better correlated with the radial distribution of density? So as the different types of ice, the clear ice, the opaque ice, those layered structures you see in natural hail, how does that affect how strong hailstones are? And so I have a nice kind of pretty image process of a lab hailstone that we produced, showing the kind of differences in the layered structure. The opaque ice shows up as the warm colors where you can't quite see through the cross-section, and the clear ice, which is more dense, shows up as the cooler colors where you can see the background. So how does that change with radius in a hailstone, and how does that affect the strength? Some ongoing research collaborations where we're working towards solving a lot of these problems. These are the organizations we're working with directly right now. Obviously, we're open to really anybody who will want to work with us on this. Texas Tech, we have 4 fixed hail impact probes on their West Texas mesonet stations, exploring the use of those platforms on a fixed weather station network. Penn State, we're working on dual polarimetric radar hail detection, as well as the Stormchasing numerical modeling of hail. So being able to actually simulate hail production within these very fine-scale models. Big implication for forecasting the hail hazard and even potentially kind of on-demand loss assessment. And then the National Center for Atmospheric Research here in the U.S. Mentioned Andy Hemsfield quite a bit. We work closely with his group on hail aerodynamics, hail microphysics, and we're even working with Andy and a professor at Colorado State aggregating some hail pad data to look at general hailstorm characteristics as well. So that's kind of the program in a nutshell, and I'll turn it back over to Tanya, and I hope you see some of the links as we kind of move through the rest of the presentation.
All right, thank you. So what I'm going to talk about is really the kind of engineering side. What factors can we test in the laboratory, and what factors should we test in the laboratory to try to understand hail losses, and then ultimately a goal would be to actually reduce those losses. So to start out, we're going to talk a little bit about building vulnerabilities and some of the components in particular that are vulnerable to hail in particular, but also sometimes other hazards as well. So if we look at this list here, these are some of the factors that we've identified that affect a hailstorm risk at a particular location or a particular property. Some of them are dependent upon the building itself, such as the materials, the age and condition of those materials, how well maintained they are, whether or not there's an impact-resistant roof. But some of the factors are more environmental and things that you can't control, such as the wind speed and direction for a storm, the hailstone size and density, and the hailstone hardness. Those are obviously storm dependent, so there's really no controls you as a person can have on those. The sheltering of a building is an interesting one. There's been claim studies that have shown that if there's a large tree, a large fence, something that can actually shield the building from the hailstones hitting it, that can actually reduce the losses. So I guess in some degree you would have a chance to be able to affect that as the person. But the one that we really focus on here in the laboratory at IBHS is really the impact resistance rating or lack of rating of roofing materials. That has a big implication in the overall damage state of a building after a hailstorm, and really affects how much damage there's going to be and how severe it is. If we look at the overall building, the components that are vulnerable to hail is basically any surface. Any surface of the house can be vulnerable to hail. Roof, siding, windows and screens, doors, any trim, railings, decks, fences, and equipment. I think a lot of people don't think about those extra pieces that are part of the property when they think about the hail risk. But decks, fences, equipment, particularly air conditioning equipment and vents on the top of your house, those things are all definitely things that can be damaged by hail. And we've seen it in claim studies and we've seen it in damage investigations. The damage modes that we commonly see, spatter marks, which is where you've actually removed kind of the oxidation or the grime that's on metal materials, whether it's an electrical box or a vent on the top of the roof. Dents in any metal surfaces, so it could be on a window frame, it could be on a gutter, downspout, fascia, anything like that. Could be on the roof surface as well. Cracks and tears, we can see those within materials, and a lot of times we'll see damage to the paint and the finish. But again, the main component that we're going to focus on is the roof. And the reason that we focus so much on the roof is that historical studies, both done externally and done by us, have shown that the #1 component that's damaged in a hail event is the roof, which makes sense. Hail is generally a vertically falling object, so the first thing it's going to hit is the roof surface. In order to be able to hit things like windows, doors, walls, there has to be a pretty significant wind that comes with it to propel it into the side of the building. So overwhelmingly, the number of losses are dominated by the roof damage. So we're just doing a quick comparison here of a study from the 1960s that showed the different property damage rates for different components from their study. And then we also did a similar kind of analysis in a claim study that we published not too long ago. And you can see that overwhelmingly in both cases the roof damage is the largest driver of losses. If we take a look at that a little bit more, so in this pie graph we're looking at on our side the damage payout by component. So this is how much of the loss dollars went to each of these components. If we look at the claim frequency, so this is the number of claims compared to the number of overall exposures in our data set, you see that not only were there high costs for the roof damage, but the roof damage also occurred more frequently than any of the other damage types that we looked at, which is a trend that we see not only for hail events, but actually for a lot of natural hazard events. The roof is often identified as a component that's most frequently damaged, whether it's a wind event, a wildfire event. It's often the roof that is driving the number of claims. And these are an example of some of the different types of roof damage that you could see. It could be damage to the roof covering itself, such as the damage shown to the shingles or to the metal roof panel in the bottom right picture. It can also be damage to roof accessories like the gutters or the vents or the fascia or some of the other pieces that are needed to keep a roof together or that are part of a standard roof construction. So all of those components are vulnerable and all of them add up into losses against the policy. If we look at a little bit of historical literature, there was a study done by engineers at Hague Engineering back in the early 2000s, and they identified what is kind of the minimum threshold size to cause damage to different roofing materials. So shingles, shakes, the wood style roofs, and looking at tiles and some other styles as well. And you'll see that the range varies quite a bit. Damage can start as low as 1 inch in diameter hail and can go up to over 2 inches for the built-up gravel roofing shown on the right side of the figure. But the majority of roof products in the U.S. are asphalt shingles, at least on the residential side. So that's where we're focusing a lot of our attention. We wanted to try to have the most market impact that we possibly could. So when we look at the overall number of materials on residential properties, it's overwhelmingly driven by the asphalt shingles. So if we can understand the performance and improve the performance of the shingles, then we would have a chance to make a big dent in the marketplace. So this is what we want to understand. We want to understand asphalt shingle impact resistance. Whether it's a regular product or an impact resistant product, this is the kind of relationship that we want to understand. We want to understand what hail sizes actually cause damage. How do we build this distribution curve for different sizes of hailstones? And it will vary by age. It could also vary by region, just because of how the conditions and exposure will affect the shingles. But underlying all this is the hail size distribution. There's some sweet spot of hail sizes that are so big and so damaging that this product, shingle, would not be able to withstand it. But if the frequency of those events is so small, that might be okay. We really want to understand what sizes of hailstones we should be working towards based on the distribution of hail that falls in an area. So what we want to understand is, when does a shingle lose its water shedding ability? What does this relationship look like? How do the effects of aging play a role? And how do we know when it's going to lose its water shedding ability? We know it's going to be affected by the condition of the roof, but how bad does the damage have to be? Can we distinguish between cosmetic and functional damage to really understand when a larger threat comes around? So the tools that we've been using to start this process is going through the standard test method. That's a good place to start the research. It gives you a baseline for all the products that are out in the industry, and gives us a way to give relative comparisons between them. So the first method that we use is a steel ball impact. This is a test that is written by Underwriters Laboratory. It's called UL 2218, and this is the official method for rating the impact resistance of asphalt shingles. You drop a steel ball of a set size from a prescribed height, and the energy that it has when it impacts the shingle is the same or similar to what a similarly sized hailstone would have in nature, based on that 1960 Lorry paper that Ian was mentioning when he was comparing some of the hailstone data. So I'm going to quickly tab through this, and you'll kind of see how the test actually works. The steel ball is dropped from a tube. It impacts the shingles. We have a laser sight on it, so we're impacting particular zones of the shingle that we think might be vulnerable. Once the shingles impact, you can kind of see the kind of damage that it might create. In this instance, we've got a small dent, and you'll notice that there's a little bit of white powdery substance. That's where we've actually crushed the granules on the surface of the shingle, which is a damage mode that occurs with almost all impacts in this particular test, but it's not a damage mode that you see in the real world. In the real world, hailstones are not hard enough or strong enough to crush the granules on the surface of a shingle. That signature can often indicate some kind of fraudulent damage or some kind of mechanical damage as opposed to hail damage. So that's something to always be aware of. And then kind of a last step for this process is we take the impacted shingles, we cut them into little sections, and then we actually look at them under a microscope. And according to this test method, if a shingle shows a crack or a tear on the back side of the shingle when looked at under magnification, that's what is considered a failure of this particular test. So we go through and we record the percentages of passing and failing for each of the products that we test under this method. And this is what the results look like. We did a study in 2014 where we compared 22 different shingle products off the shelf. So we just called the local distributor and ordered and had them delivered here. And we tested these to see how they performed against that test. So on the left side of the screen, we're testing a standard 3-tab shingle versus an impact-resistant version of the 3-tab shingle. And what you see here is that the impact-resistant shingles definitely perform better than their 3-tab counterparts. On the right side of the screen, we did the same series of testing, but we tested a standard architectural product, and we tested impact-resistant architectural products, and then a premium architectural product. Now, those premium products are generally marketed for aesthetic purposes, to give a kind of richer, high-definition look, but they sometimes are thicker and heavier than a basic shingle, so we just wanted to see if there was any performance difference with that increased thickness and weight. And what we saw in both cases is that the impact-resistant shingles, while they did perform better than the basic products or even the premium product in the case of the architecturals, we still weren't seeing passing percentages at the rate that we wanted. Every product that's categorized in this impact-resistant 3-tab or this impact-resistant architectural, every single product in those categories is rated to pass up to the Class 4 level, which means that all of these bars, the blue, the orange, the green, the yellow, every single one of those should be at 100% for this particular test. And we found that it wasn't. So we did a little bit of investigation. We talked with Underwriters Laboratory to try to figure out what was going on. And we found that the way that we test it is the same way that they test it, so it wasn't a difference in the testing capability, but they're testing a product that's brand new off the factory line, whereas we're testing a product that we got from the distributor, so we have no idea, where it came from, how long it sat on the shelf before it got to us, if it sat in the sun, if it sat in the cold, if it sat in the rain. We don't understand any of those things. And we know that as products sit, they actually become more brittle. So the longer and longer that it's sitting before we get our hands on it, the more brittle it becomes, which makes it more prone to cracking. So after we talked with them, they recognized through our research and through their own research of market surveillance of off-the-shelf products that the testing frequency wasn't really capturing the true off-the-shelf product performance. So Underwriters Laboratory has actually increased the frequency of their physical testing. They used to do it when a product was first submitted, and then they may not go back and test it for many years. They've actually changed that process now so that they're testing it every 6 months to make sure that the product, at least off the factory floor, is actually passing this test. The next step in our mind is to try to understand, what changes between when it leaves the factory and when it gets in our hands or on a homeowner's roof. But we wanted to take this a little bit further. So we knew that we weren't getting quite the results from the impact-resistant shingles that we were hoping for. So we actually broke the impact-resistant shingles into 2 categories. One of them is a traditional impact-resistant shingle, which features a mesh or a scrim on the back side of the shingle. That's how it gets some extra rigidity and theoretically passes the test. And then the other way to get an impact-resistant shingle is to actually do a chemical modification of the asphalt itself. And you're adding polymers to the asphalt, which makes them more flexible, more stretchy, a little bit better able to absorb the energy, was the hypothesis. So when we put those statistics together and broke them down in that way, we did notice that the polymer modified shingles did have higher passing rates than the traditional impact-resistant shingles. They're still not at 100%, but we did see an increase in those quantities. So the next step of our testing, once we wrapped up the steel ball testing, was to take it one step further. We got a good way to give relative comparisons between the performance of shingles, but we wanted to try to tie it a little bit better back to real-world performance. And that's where the ice ball testing comes in. We recognize that some of the damage modes that are created by the steel ball drop test, so again, it gives us a great way to do relative comparisons. The damage modes are not really representative of what claims adjusters are seeing or homeowners are seeing on their actual roof. So we took it to the next step, which is the ice ball impact testing. And we started with the FM 4473 standard, which, as Ian mentioned, is a pure water ice ball test. And it's at the high kinetic energies. And we started there, and we went through the testing sequence. And this test is pretty simple to perform. This is a couple of shots of some of the impacts that we actually could create. So it kind of gives a nice view of what this looks like. And these are the kind of damage patterns that we were able to produce in that study. A lot more granule loss as opposed to crushing those granules, which is definitely more representative of what you'd see on an actual house. You'd still get sometimes the denting, the cracking, the tearing that we saw with the UL test, but the behavior of those granules is what was really encouraging. However, there's still some concerns with even the standard ice ball test method. Whether we tested it with steel balls or whether we tested with ice balls, we still didn't get any of the products to pass with 100%, which is definitely concerning. So we're doing a bit more research into that. In addition, I already mentioned that the damage modes were not necessarily realistic. The ice ball was definitely better than the steel ball, so we're continuing along that path. Ian showed you that the kinetic energy curves that were used in the standard test method and developed in the 1960s are a bit high compared to what we see in the real world. So we've also been doing some work by changing the ice that we create and changing the kinetic energy that we fire the ice balls at, or changing the velocity so that we can change the kinetic energy. And we're hoping to try to hone in on the right damage patterns. So we're getting the right damage modes with that FM test, but we want to try to make sure we get the right severity. So you can kind of see where we're going with that kind of testing. We've also seen inconsistencies in the ice balls that are produced in the standard test method, so we're trying to improve that process. And then the last point is both of the standard test methods only address the performance of new products. So ones that have not been exposed to the sun, have not been exposed to snow events and rain events and all the other things that a normal roof undergoes when it's installed in the house. And if you compare the pictures on the left side to that on the right, you can see that the way that the damage looks is different. So we want to try to build the connection between new performance in the laboratory and what it means longer term. So I'm going to turn it back over to Ian now, and he's going to talk a little bit about some of the ice improvements that we're making to try to address some of these concerns.
Thank you, Tanya. What you're looking at here on the screen is perhaps the most sophisticated ice machine on the planet at the moment. It's a very large system. It was geared. We haven't talked much about full-scale testing, but if you know a little bit about the IBHS Research Center, we do have a very, very large full-scale test facility, and we can do full-scale hail simulations in that. So we needed to produce a large amount of laboratory hailstones as well as consistency amongst those laboratory hailstones for repetitive testing. And we talked a little bit about the variability in that the FM standard ice ball versus some improved testing. And so what we've ended up with is this system. It's about 3 years worth of research and development, and it is designed to produce a very consistent ice stone in mass, so a capability of producing upwards of 1,000 of a given size per day. It's quite a sophisticated piece of equipment. We actually use diffused carbon dioxide gas that is injected essentially into water that's up in those big tanks up at the top of the system. That helps us introduce a bubble structure and drop the density closer to what would natural hail be. And I'll show a couple of examples of kind of the ice that this system produces. It's a very rapid freezing process, and with that, we produce probably one of the most remarkable laboratory ice cross-sections I've seen or been able to do. We actually mimic some of the same layering structures that a natural hailstone exhibits Well, the process is quite different. We work from the outside in. A natural hailstone is collecting ice particles, collecting supercooled water, a very, very different process, but we actually managed to mimic some of that through a rapid freeze. We freeze a 6-foot slug of ice in the system, so coolant is circulated in a jacket around the liquid. It's frozen in about 40 minutes and then extruded, and then we use heated molds to actually shape the sphere. We use spheres, highly repetitive when we're shooting them out of an air cannon, so we get consistency in terms of the velocity. And you can work backwards to do equivalent diameters of natural hail based on field research historically, as well as the database we have. So spheres are very repetitive. We do have the capability now that we're collecting 3D models of hailstones to make molds to match those to look at some of the shape effects, but I think we're a little ways away from tackling that. But the neatest image is that bottom right, showing a cross-section of natural hailstones. So the hot colors are the opaque ice that have a lot of bubbles. The cooler colors are where the background shines through, and it's a lot more clear ice with very little bubbles. And we see the example of a natural hailstone, one we produced in the lab, and then the FM 4473 clear ice. And you can almost get a feel for some of those microfractures that may happen in the middle of it in that core of the cross-section. So we're actually able to reproduce some of the same structures. We've actually reduced the amount of spread in the strength using our system by a factor of 2 compared to the FM injection mold method. So we're getting very good replication in the ice stones we're producing, which is vital for those impact tests. And kind of where that leads us is to the full-scale research is testing new and aged specimens in our big, large-scale test chamber. This gives us the ability to simulate a hail event on a roof system or a structure, a complete structure. We can look at repair and replace methodologies to mitigate the damage. We look at age effects. We can see if water enters the structure after a hail event or if it's aged for some time. So it gives us the ability to look at all these different factors for a building system as a whole. And then we can provide a degree of guidance on the best practices. So with that, I'm going to turn things right back over to Tanya.
All right, thank you. So a couple of things to kind of close us off. One of the projects that we're working on is trying to address this aging and weathering thing. You heard us mention it a couple of times. The testing that we're doing is focused on new products, but obviously as soon as you install a product on a roof, it's being exposed to sun and wind and rain and hot temperatures and cold temperatures and all of these different things that a roof has to undergo. And we want to understand what the implications of those factors are on the performance of the roof material. So we've constructed an aging farm. This is a viewpoint of our aging farm at the end of 2014. We actually have expanded it so that there's now 60 small roofs on our farm in South Carolina. And what we're doing here is we're just letting them age. They just sit there, and they get the sun and the rain and the wind and all the things in our South Carolina climate. And we've designed this experiment to try to understand which variables and how those variables control the durability of the shingles, how long they're going to last, and how they're going to perform when we test them. You'll notice that the roofs are grouped together in groups of 4. We did that so that we can pull samples at 5, 10, 15, and 20-year increments. So we'll pull from one of the specimens at each of those 5-year periods and actually do wind and impact testing in our laboratory. When we designed the experiment, these were the variables that we thought really played a role in the performance of the shingles over time. So one is obviously the climate. So in addition to our farm here in South Carolina, we also have smaller subsets of farms in Ohio and in Wisconsin, and we are hoping to expand to a couple of other locations over the next few years because we recognize that the climate will mean that these roofs experience different kinds of conditions, and we want to understand how that plays a role. The in-service length is being addressed by trying to pull samples every 5 years. We expect that the performance will change over that period, so we'll be able to evaluate that. We think the direction of the sun exposure plays a role, so all of our buildings, both on our farm and at the remote farms, are pointed such that one face faces north and one face faces south. And we do see some differences on those. it's harder to seal the shingles on the north side because they don't get direct sun exposure. There's often more moisture or more dew that collects on that side. It doesn't burn off with the sun. So we're monitoring those kinds of conditions. On the material type, we're focused purely on shingles, but we've got different kinds of shingles, different brands, different types, whether it's 3-tab or architectural, or if it's impact resistant or non-impact resistant, if it's that polymer modified or traditional impact resistant. We're trying to capture all of those different pieces. On the material color, for the most part, we're trying to hold this fairly constant, although manufacturer to manufacturer it varies. But in the future, if we wanted to look at differences in color, we certainly could do so. Right now, we're also holding the roof pitch constant, but it's something that we could vary in the future if we wanted to do so. And all of this, once we build these kind of vulnerability curves associated with this, plays into the factors that are shown at the bottom: the underwriting, the duration of incentives for impact-resistant roofs, how you would handle claims if you have an understanding of what the damage looks like at different age periods. It helps distinguish real damage from perhaps maintenance and aging-related issues, and of course risk modeling. And I should mention that all of these farms are instrumented so that we're constantly collecting information on the roof. We collect temperature at various points on each roof so we can monitor how the roofs respond to changes in weather. So each of the locations also has a weather station, so we know when there was a large rain event. We know when it was a really hot time period or a really cold time period, and we're correlating all that information with the conditions on the roof. In the history of this project, we've measured temperatures on the roof over 200 degrees Fahrenheit, so it gets incredibly hot on those roofs. And we've also seen instances where cloud cover, passing clouds, can change the temperature 30, 40 degrees in a pretty short time period, which puts a lot of stress on the product. So we're monitoring all those things to help understand the performance. And what we're really trying to understand is, how does the climate play a role? At what point do the IR shingle performance degrade? Is there a point at which they're just the same as the basic shingle, or are they always better than the basic shingle? We want to understand that. We want to understand how the sealant is affected by the climate and the aging. Does it always seal initially? Does it become unsealed at any point? And that has big implications in the wind side of performance in particular. So we're trying to understand these factors. Are there ways that we can model these such that we can develop vulnerability curves that really predict the true performance as these are expected to perform in their life cycle? And can we use imagery? Can we use imagery sensors to actually determine the age and conditions of shingles? Those are some of the more exploratory areas that we're looking at. So where does all of this good information land? As we start to understand the performance of shingles, where does it go? Well, obviously we give the information out to our membership. We also communicate with manufacturers of products so that we can share information with them. If we learn something about their product, they could make a change if they wanted to. They could change their formulation, they could change their installation, they could do nothing, but we try to always give the information in case there's something that they want to do, because really for us it's all about improved performance. Improved performance makes life much easier for homeowners, and it reduces the losses for insurers, which is a big deal for us. But the other place that it can go is our Fortified Home program. This is our Code Plus construction program, and we actually have a standard for hurricane performance and for high winds and hail. So, of course, that's what we're kind of focusing on with our particular results out of the hail research program. The hurricane program is focused on the coastal parts of the United States. The high wind and hail is really the interior part. And this is a systems-based approach, and it's a tiered system. So there are some steps you can do at the bronze level, which are really focused on the roof system. There's steps at the silver level, which kind of take it the next step forward and actually focus on some of the attachments for different buildings. And the gold level, which really starts to focus on the structural load and how you keep the structure tied together. So for hail, the number one guidance that's available is the application of an impact-resistant roof. So you can get that hail protection or that strengthening or mitigation against the hail hazard right at the bronze level. Again, this is a voluntary Code Plus construction program. We just launched the High Wind and Hail program in Tulsa, Oklahoma back in February. So this is a new standard, and we're trying to grow this in the center part of the country. And this is kind of where our focus areas are. I mentioned the hurricane part of the program is on the coastal areas. The high wind is focused primarily on the west part of the United States, but also some of the more northern and eastern climates. And then the high wind and hail is really most of the center part of the country. It includes Tornado Alley, it includes Dixie Alley. If you think about extending this into Canada, this would be right along your Central Plains area as well, in the center part of Canada. So really, those are the areas that commonly experience the larger and more frequent hailstorms. Those are the areas that we will really want to try to focus people on considering the application of an impact-resistant roof. It definitely gives more protection than a basic product. Again, we're trying to understand what the long-term performance of those products are and how the laboratory testing really relates to the actual real-world performance, but it definitely is the best practice that's available at this point in time. I mentioned that we have collaborations with several roofing manufacturers. Again, as we learn things in the laboratory, we share the results with the manufacturers of a particular product so that they can use that information, use that research back in their manufacturing situations or their business situations to try to improve the performance. For the most part, the asphalt shingle industry, several of the manufacturers which are represented on this screen, have been really great to work with. They're very open and honest about their products. They're very receptive to hearing what we're up to and what kind of results we're getting. I think they recognize that for the health of the shingle industry, they need to be proactive in actually trying to understand some of the issues that face their products. We know that the threshold for damage for some of the other roofing products is a little bit higher, so I think these guys recognize that there's some benefit in trying to improve performance to keep their market healthy. And we also have collaborations with several industry associations on the metal building side and on the asphalt roofing side, the single-ply roofing membrane industry as well. We also collaborate with the National Roofing Contractors Association, as the contractors play a really big role in this. Anytime we're talking about code plus construction, we're asking the contractor to do extra steps. So they're definitely going to play a role in making sure that things are done correctly and that you're actually getting the additional strength that you're asking for. And the last one that I'll mention is RCAWI, which is the Roofing Industry Committee on Weather Issues. We have been working with them for several years to develop some best practices guides. This is bringing all of the industry associations to the table. So it's a partnership between us, RCAWI, and several of those industry associations on the previous slide, and several others, the tile roofing industry, the Cedar Shake and Shingle Bureau, several others that are at the table with us, and we're trying to bring all of the information to one place. So the best practices guides focus on the installation of roofs, the maintenance, how you would go about identifying damage and determining if it was from a particular hazard or if it was natural aging or if it was maintenance related. And then once you've identified the damage, how do you make a recommendation for repairing or replacing that damage, and how do you identify what product was in place or installed so that you can match it or put it back to its previous quality. When we started down this road, the primary audience that was identified was claims adjusters who really wanted some great guidance from the roofing industry to make sure they knew what they were looking for and how they could recommend the best practices or the best repairs for their clients. But what we found as we started down this path is that there were several other audiences that were identified. Inspectors, code officials, contractors, consultants. There's lots of people who could benefit from having all of this information right in one place. There's really no one's trying to promote their one thing. We're trying to get all of the right information in one place so that you don't have to go to all these different places to try to understand what the best thing to do is and how to identify the damage and repair it. So we're bringing all those groups together to try to accomplish this. We have completed several sections of the guide, and we're starting to build a web framework for this. We wanted to make it an electronic format so that as things change and as we learn new things, as codes change and all those kinds of things, we could actually update it without having to reprint big manuals. So we're working on the framework for a website now. We're hoping to be able to launch this within the next year or two. We're really getting all the pieces put in place to be able to bring that forward. So with that, I'll go ahead and close the presentation out. We have a lot of videos that are available on our website. They're not really easy to show in a webinar format. So if you want to see some of the videos of some of the testing that we described, you can see it at our website, disastersafety.org. If you have any questions after the presentations that you'd like to email us about, please consider doing that. We also put our Twitter handles up on the screen. We are going out into the field to do our next field measurement campaign starting in May. And anytime the team is active in the field, you can follow our updates using my handle, Ian's handle, or at IBHS Hail Study is the overall project. So please consider following us on Twitter if you want to keep up with the team while we're in the field. Thank you very much.
Excellent. Thanks very much, Tanya and Ian. Very amazing work going on there. Very interesting stuff. So we have a number of questions that have come in throughout the presentation. Audience members, feel free to submit more questions when you have a chance. First question, which I think I'll sort of paraphrase. So you guys are looking quite a bit at sort of the mechanical damage that is associated with hail. Is IBHS or anyone else you know of working on sort of translating that damage into actual claims reduction or property damage loss reduction? So for example, how does traditional claims associated with traditional shingles on houses compare to the impact resistant shingles?
That's an excellent question. We did a claim study back in, well, we started it in 2011, and we actually put out a journal publication on it in 2015. And that's a study I referenced where we looked at the different damage distributions, damage frequencies, whether it was the roof or the walls or the windows. One of the fields that we attempted to study through that particular research project was to understand the performance of traditional shingles versus impact-resistant shingles. That was one of the goals of the study. What we found as we went through the process was that the number of impact-resistant shingles within the data set was fairly small, but in addition, there were a fair number of roofs where we didn't know for sure if it was impact-resistant or if it was a basic shingle. So without having that information, we really weren't able to effectively answer that question. It's definitely one of the hot topics on our mind. We'd love to be able to answer it. There's some data issues that would need to be resolved in order to study it, to try to answer that question in a future study. One particular area that we've been kind of exploring to see if we might be able to take another route to understand it is a cost-benefit analysis. We want to take the laboratory results that we're getting on these different kinds of shingle types and pair it up with the frequency of different sizes of hailstorms or the frequency of different events that have certain sizes of hailstones, and try to understand where it might make sense to have impact-resistant roofs based on that frequency and severity of stones, and make sure that it's an economical decision. If there's a location that's constantly getting, I'll exaggerate and say 5-inch hailstones, impact-resistant products are not designed to meet that. So we really want to focus on what areas, really could benefit from having these products in place. Do you want to add anything else, Ian?
No, that's a pretty good description. It's really the balance of the event frequency and the actual performance, and really trying to provide some kind of real guidance for consumers or even our membership too as to how they should approach it.
Great, thanks very much. I had actually a couple questions about the roof farm that you're working on and age of shingles and so on that seem to have a big impact on their impact resistance. So you mentioned that when you're testing shingles, there's some unknown factors like how long they were sitting in storage, and that might affect their strength. When you built your wind farm, were you using shingles, straight out of the factory, delivered directly to the lab, or were they bought from, distributors and it might be a little bit on the old side? And it is sort of a related question. So you said that you're going to look at different sort of time spans and test shingles, so over 5, 10, 15, 20-year time spans. And some of the sort of marketing that goes along with shingles is that they would, last 30 years. And I think we probably pretty widely know that that's not the case. But do you have a sense about how old, on average, shingles are on homes? So two questions, one related to the age of the shingles that are on the testing farm and how old the sort of average age of shingles are on homes out in the field.
Okay, excellent questions. So I'll start with the roof aging farm. Every product that we test, no matter what the project is here at the lab, we always purchase the materials from a local distributor. We want to get the same kinds of products that a homeowner or a business owner would get installed on their job. So we purchase everything through the distribution chain. So all of the shingles that are included on our aging farm have been through that distribution chain. In general, I'd say usually when they show up at our facility, they're generally less than a year old. We do actually collect the packaging code information, so we can work with the manufacturer to trace back when the particular shingles were produced, so we can get a little bit of a handle on that. But we do get everything through distribution. In an overall sense, I think the amount of exposure that we're putting on the roof farm, at least 5 years, will overwhelm how long the products actually sat on a warehouse floor or out in the storage yard. I think for the aging farm's sake, that will definitely be the case. When we do laboratory testing of brand new product, well, brand new in quotes product, that variation might be a little bit more significant. But I think once you put it out in the sun, out in the regular climate for several years, I think that probably dominates the answer. In regards to the question about how old do I think the average shingle on a house would be, that's a hard one to answer, and I think it probably varies by location. There's a lot of markets, I'll say Dallas, Oklahoma City, kind of in that area, where they have significant enough hail events that the average roof is probably less than 10 years old, just because they're replacing it so much. I have friends in some of those locations who have gotten 3 new roofs in 5 years because of hail. So the age can definitely be a bit lower if you're constantly replacing these roofs. Now, there's some locations in the U.S. Where roofs are probably a fair bit older than that. Here where we're at in South Carolina, we have a lot of new construction, so there's obviously new roofs there. But there's a lot of buildings that have been here for a very long time, and you can tell that the shingles are very old. So it's difficult to say. I think it depends on how much growth there is in a particular area and how often roofs are being replaced for natural events. I think a lot of people, unfortunately, rely on the insurance industry to buy them a new roof instead of actually replacing an old, worn-out roof. So some people really push how long they're going to stay on a roof.
Okay, great. Thanks very much. Another question that came in over the webinar related to that sort of comment that you had earlier about fraud and how you might be able to identify fraud with the ball bearing test, which resulted in crushing of granules on the roof versus when you're firing the ice balls on roofs, you see more of a removal of granules rather than crushing. Would you say that's a good indicator of fraud, or how reliable would that be?
I think that's definitely a good indicator of fraud. Anytime you've got crushed granules, you should definitely be asking some questions because hailstones really don't have that damage mode. They'll knock the granules off, but they don't really crush them. So that often is indicative of fraudulent damage or intentional damage. A couple of other things that you can look for with regards to fraudulent damage is patterns of damage or regular occurrence of damage. A lot of times you'll see that fraudulent damage is only in the center part of the shingle, or it's only in the area that you could reach from a ladder, or it's fairly evenly distributed. Real hail is random. It's not going to favor a particular area. It's not going to only hit the center part of the shingle. It's random, so it's going to damage would be seen in lots of different parts of the shingle and lots of different parts of the roof. The only exception I'd say to that is sometimes depending on if there's a shielding of a particular roof face or if there's a significant wind component, you may only have one face of the roof damage while the other one really gets just kind of glancing blows and doesn't show a lot of damage. But other than that, if you see any patterns of damage, that can often be indicative of fraud if it's kind of a regular pattern, a repeating pattern.
I just wanted to chime in real quick on the fraud reduction side. The improved event characterizations are going to help as well. The better we get at radar hail detection, especially with dual polarimetric radar, and even some of these computer thunderstorm simulations where we could even use it in a hindcast situation. And you couple that with, say, our laboratory damage functions or a damage simulation, we'll know what type of expected damage you should see per age of product, per type of product. And I think the potential is there to know when you need to scrutinize an event or a situation much more to try to reduce the fraudulent effects.
Great, thanks very much. A question about the traditional impact-resistant shingles that use a mesh versus the polymer-modified shingles. There was a question about whether or not the polymer-modified shingles are widely available. Perhaps, I don't know if you can comment on Canada, and if there's a significant price difference between these two products.
Okay, another excellent question. The product availability, we've actually seen a shift in the really not long ago. It used to be that the mesh or scrim on the backside of the shingle was the way to create the impact-resistant shingle. Then you had a couple of manufacturers start to kind of dabble in the polymer modification of asphalt to try to improve that flexibility and resiliency. And actually, just last year, one of the major manufacturers started producing a polymer-modified shingle, and that actually signified the shift. If you look at the top 7 manufacturers of shingles, when that guy jumped on the polymer modification train, it actually shifted so that more manufacturers produce polymer-modified shingles than just the traditional impact-resistant shingles with the mesh. So I think you're seeing the industry respond a bit to this. There are still several major manufacturers that only produce a product with a scrim, but many of them are producing the polymer-modified shingles instead now. So it'll be interesting to kind of track to see if that trend continues. If the results that we're showing are real, then I think you will see that. Our sample sizes are fairly small, so we're doing a lot more research to try to understand the performance of polymer-modified shingles in particular, because they showed indications of better performance. We really want to understand that. If that trend is real and continues, I wouldn't be surprised to see more manufacturers switch over. But it's not an easy thing. It's a major overhaul of your infrastructure and your machinery, so it's not just flipping a switch. But it'll be interesting to monitor. In regards to the cost, impact-resistant shingles are pretty much always more expensive than regular basic shingles, but a price distinction between traditional and polymer-modified, it's not huge. They're pretty similarly priced. Now, your individual marketplace is going to cause variations. Like us here in South Carolina, it's fairly expensive for us to get impact-resistant shingles because none of the plants near us manufacture those. We're not really in the main hail belt of the country. But if you're in a location like Dallas, there's a plant right there. So I think you get a little bit lower cost. Ian's done some research on some of the pricing. Do you want to add anything else?
Yeah, the difference between the polymer-modified impact-resistant, and we have a relatively small product sample size there versus traditional impact. It was a less than 15% difference, so it's fairly comparable. And yeah, if you look at just bolt pricing, taking out the supply chain, yeah, they're pretty comparable. But once you start adding in some of the shipping costs, like Tanya mentioned, so it's kind of regionally dependent. We compiled some of these statistics, and you can actually see some of the pricing shifts with different markets. I think that's what drives some of the cost differences. In terms of availability, when I hit up about 8 different supply groups, whether it be your big box store or bulk supplier, most could get them. The availability, especially in the central U.S. of the Great Plains, they were available. You could get them, and we found that here. It's just the shipping costs may fluctuate, and that's where some of the pricing differences comes from.
And I suspect that would probably be the biggest implication for the Canadian market is if you have to ship it over the border for impact-resistant shingles. One of the major manufacturers, IKO, produces an impact-resistant shingle, and they do have plants in Canada. I'm not sure if they produce the impact-resistant shingles at their Canadian plants, but I think CertainTeed might have a plant up there too for Saint-Gobain, but I don't know specifically availability for the Canadian market, but that's I would assume that any shipping over the border would cause an increased cost, but you may be able to get them more locally.
Excellent. Thanks very much. Maybe we have time for two or three more questions. One question again about the testing, the hail farm testing. I know you mentioned that you're going to be setting up roof farms in Wisconsin and Ohio as well. But I suppose they're not up and running yet. So a lot of the damage we get in Canada, of course, is in Alberta, southern Alberta. Do you have a sense about how cold weather climate might affect the impact resistance of shingles and how, I guess, sort of appropriate the findings will be for the South Carolina testing for Canada?
All right, excellent questions. The farms that we have in Ohio and Wisconsin actually are active. One of them was completed in the fall of 2014 and the other was completed in December of 2014. So they are both up and running and have been running and collecting data for about a year and a half now. So we're excited to have those opportunities. Both of those farms have a smaller subset of the products that we have here on our farm, but we knew that cold weather was potentially a big risk to asphalt shingles. We talked a little bit about kind of the thermal cycling. We would see temperatures over 200 degrees and then a cloud would come by and it dropped 30 or 40 degrees. That temperature cycling, those big swings, is something that we're really concerned about because it causes expansion and contraction in the product. So I think a similar thing could be said for the colder climates. When you go from above freezing to below freezing and you do that kind of cycling, we have a hypothesis that that could actually make the product more brittle as it goes through those cycles, which if you're thinking about impact performance is very significant. A brittle shingle will have a hard time passing the test that we perform as opposed to one that's more flexible. So we think that there are some implications. We don't know what they are. We don't know how bad it is. We don't know if there's some magic number of thermal cycles or freeze-thaw cycles that makes a difference. But that's why we built that farm, to be honest, is to try to capture information for climates that are much colder than us. We're also trying to target some other regions to build farms so that we can get some additional variation. We recognize that results from those northern climates and just our one in South Carolina doesn't paint the whole picture. So we're trying to find partners that might be able to help us build in a couple of other locations in the U.S. In terms of applicability to the Canadian market space, I think the results from the Wisconsin farm would certainly be the most applicable to you guys. You'll have similar kinds of weather in your plains areas as we do in our upper plains in Wisconsin. So that would be the one that would have probably the closest tie. I mentioned the brittleness with regard to impact resistance, but there's also some implications on the wind side. So shingles have a sealant that actually helps them perform against wind. The sealant will seal the layers of shingles together. If that sealant is compromised, that's when you get a large amount of shingles lost in a high wind event. So again, as you think about freeze-thaw cycles, if that sealant expands and contracts and eventually breaks, then you're much more vulnerable to the wind hazard as well. So we've designed all of these farms so that we can test the panels for both impact resistance and for wind performance, because we recognize that as that sealant is affected, there could be implications in the wind performance as well.
Okay, great. One last question. Have you looked at auto hail damage as well? It seems like a lot of the work that you're doing on roofing materials would be appropriate for auto losses.
We haven't specifically. here in the U.S., kind of our sister organization is the Insurance Institute for Highway Safety. We've discussed that, and we hear about a lot of mitigation strategies. I think in the short term, what's going to help on the auto side is going to be improved hail forecasting and detection, such that people have adequate time to say, get your car in a garage or under cover, or if you know a day has a high probability of a hail event, to keep the car in a garage or something like that. We haven't done any specific testing. However, I wouldn't say that we're not open to that, and we just haven't been approached really by the right group, I guess, yet to start down that path. We've been asked by our members to focus on roof systems, and that's where we've been.
Okay, great. Thanks again for the presentation. Really incredible, comprehensive work going on at IBHS that will continue to follow as it develops. Thanks to all of you who participated online and submitted questions. If you want to tune in for our next webinar, check your inboxes. We'll have our yearly wildland fire and hail forecast webinars coming up in May. And once again, I'd like to thank Tanya and Ian for an excellent presentation. And as they said, if you have additional questions, they have their email addresses up on the presentation now, and you can watch out for a recording of the presentation on our website. So again, thanks very much, and this concludes the webinar.
Thank you all.